Which I'm going to speak now. And the topics to be covered are summarized here, research one by one. It is coming on the screen. You can see research who are avoiding misconduct, plagiarism scandals, real-life consequences, and the oral and poster presentations and publication, how it should be done, and then conclusions. So, since this conference is attended by students, both MSc or post-MSc students, PhD students, so most of the contents of this talk will be for them, actually. So what to do after MSc? If it is physics, the best career opportunities, as you can see here, physics is so interesting that it is widely used in many applications. So it is applicable in nearly all areas of science, including materials, nuclear energy, electronics, statistics, particle physics, engineering, medical physics, biophysics. So after MSc, so solid state physics, materials, nuclear physics, medical physics, and in nuclear physics alone, you can see there are many branches you can work on. Nuclear power plants, since established in our country, so research on this will be useful. Nuclear energy research centers, medical research, nuclear physics lab. So in PhD, decide what type of course you would like to pursue for career. First, also in material science and engineering, research include biomaterials, ceramics, composites, energy, magnetic materials, materials for electronics and photonics, materials synthesis and processing, materials theory, computation and design, nanomaterials, and so on. So PhD journey, if one does it, and beyond this journey, what are expected of? The PhD supervisors, research topic, you have to decide. PhD work, what are the engagement, thesis writing, research presentation in seminars, research publication, and ethical behavior in doing PhD and afterwards in publishing papers. So during the PhD journey, so normally a successful PhD candidate has studied a particular area within a subject for 3 to 4 years, as expected. He has made at least one or new findings, or at least one contribution to the knowledge, written a thesis, placing their own independent novel contribution in context, comparing it critically with other approaches, and defended the thesis in the viva, which is a discussion examiners who are experts in the area. So these are other during the PhD work you have to face. So work intensively by the PhD candidate, and PhD journey during you have to write a thesis. So one should remember, PhD may have written one document at master level, but during PhD it is much more involved. PhD thesis spans much longer time scale. It requires more care than previously written thesis. What should be the structure of the thesis? So these are the things, usual things: motivation, related work, experimental data collection, analysis, conclusion. Of course, there are many variations to this core work. So during this work, focus on your primary task. Develop your own program. Your job is research. Engaging in other works will delay completion of the thesis problems. For students doing PhD actually, and even larger cost, you will fail to write a really good thesis. As a PhD student, your time is very valuable. Treat it that way. Presentation, you have to present your work, seminars, whenever possible. Writing matters, you have to think about it clearly, and more on presentation. So these are the things why much on your creativity, inspiration, your insightfulness and energy. So the topics actually main topic is the research ethics in doing PhD work or publishing paper. It is important to know what constitutes ethical research. Some persons are familiar with it, but most of them are not familiar with these things. So I'm presenting these things. All researchers should be with the basic ethical principles and have up-to-date knowledge about policies and procedures. The duty lies with the researcher to seek out and fully understand research ethics. All parts of research projects, from the project design to submit the results for peer review, have to be outstanding in order to be considered ethical. So it is writing a thesis paper poses challenge in gathering literature and providing evidence for making your paper stronger. Drawing upon previously established ideas and values and adding pertinent information in your paper are necessary steps. These done with caution, without falling into the plagiarism. Research misconduct, what does it mean? What are the components? Plagiarism, fabrication and falsification of data, careless or biased reporting and reporting data, conflicts of interest, authorship, copyright violation. So, what is plagiarism? It's the main thing. It's a cartoon here. This fellow has failed, so and asking the teacher, what do you mean? What do you mean all my facts are wrong? And still going on to say, I copied everything straight off the internet. So this is the confession, and plagiarism starts from here. It is defined as appropriation of a person's ideas, processes, results, or words without giving appropriate credit. Duplicate publication is defined as an article that substantially duplicates another article without acknowledgement, where the articles have one or more authors in common. But this does not include honest error, conflicting data, difference of opinion, or in interpretations or judgments about data or experimental design. So research ethics, plagiarism, there is something more on it. Considered as this plagiarism is considered as a serious academic and intellectual offense. You must remember, plagiarism can have highly negative consequences such as paper retractions and loss of author credibility and reputation. It is currently a grave problem in academic publishing. It is thus imperative for researchers to increase their understanding about plagiarism. more research misconduct, fabrication, and falsification. So the term actually finds these things. And several types of plagiarism include the wholesale, conscious or intentional, patchwork plagiarism, idea-based plagiarism, self-plagiarism, accidental plagiarism, mosaic, sprinkle, unintentional plagiarism, or bad paraphrasing. Paraphrasing is the, in Bengali, shabdantarito kora. Some may be familiar with this. They paraphrases or summarize another's work without citing the source. Even changing the words a little or using synonyms but retaining the author's essential thoughts, sentence structure, and or style without citing the source is still considered plagiarism. Paraphrasing, actually, I'll define what does it. The paraphrases or summarizes work without citing the source. Even so, now I define the wholesale, direct, copying, conscious or intentional plagiarism. So copying is an entire source or a large section of a source and passing it off as own work. Deliberate misrepresentation of someone else's material as own. The form of plagiarism is subject to the most severe academic punishment. Don't do it. Examples: intentionally copying another's work. If someone else write your paper for you, claiming copied material in your paper as your own. If you copy someone else's work and put your name on it, you have plagiarized. The most well-known and the most common type of plagiarism. Patchwork. What does it mean, patchwork? So you can see, going into the text, patchwork, in your text, something from some other's work, putting as a patchwork. This occurs when the plagiarizer borrows the phrases and clauses from the original source and weaves them into his own writing without putting these in quotation mark or citing the author. So next is the idea-based plagiarism. So idea is getting ideas, presenting some unique interpretation, theory, or analysis as one's own. This constitutes plagiarism even if the wording has been changed. Unintentional plagiarism. So, of course, failure to cite properly missing information, errors in publication. Failing accidentally to provide sufficient information at the source from which you have used language and or ideas. Failing accidentally to differentiate between your words and ideas and the words and ideas that you get from another source. Making errors in the placement and use of quotation often unintentional. So, two boxes, intentional plagiarism and unintentional. So, on the left-hand side, so you have to cut all this down. Copying a friend's work, buying or borrowing paper, cutting and pasting blocks of text from electronic sources without documentation, web publishing without creators. Unintentional careless paraphrasing, code documentation, quoting excessively to use your own voice. So this is a paraphrasing. So this is the researcher say, what's the big? If I change the words, I'm okay, right? He's asking question. But the supervisor says wrong. Paraphrasing original ideas without documenting your source is plagiarism too. In paraphrase, your goal is to rewrite a statement into different words and with a different sentence structure without losing the original meaning of the text and while maintaining the same general length as the original. This is another thing. Paraphrasing only. This is an example. Since time is less, so I'm going to into detail. Original text. You want to paraphrase this thing. Paraphrase. These are the text. Here, students frequently overuse direct quotation in taking notes, and as a result, they overuse quotation in the paper, etc., etc. So, in this text, it's a good paraphrase text on the right hand side. If you get a document, you can see in the how to write a paraphrase a text after paraphrasing. At best is to stay away from direct plagiarism is defined here, writing someone else's word for word without appropriate citation. Self-plagiarism is using your own previous paper, fully or partially, and reproducing it in the new assignment without permission. Accidental plagiarism, so you have to keep away from all these evils. So, an advice, I think everybody knows, or most of them knows, the plagiarism checker. There are free on also you can. So this is one address you can check 100% free online tool. Best plagiarism. If you write paper, you can check yourself before sending it to editor for publication. So another one is the so that the note. So if a research plagiarizes the work of others, is bringing into question the integrity, ethics, and trustworthiness of the sum total of his or her research. It is both an illegal act and punishable, considered to be on the same level as stealing from the author that which he or she originally created. Research manuscripts with problems are rejected. So, misconduct, what you can say, know those things. Misconduct includes fraud, less or biased recording or reporting, mishandling of data, incomplete reporting of results. Fraud is deliberate falsification, misrepresentation, or plagiarizing of data, findings, or the ideas of others. I'll give you some example, real life consequence of plagiarism. It happened. There are many examples. You can see sooner the ethical violations get exposed. You must know this. One example is science article 24th 2002, West this pioneering physics papers under suspicion for data manipulation. So is it worth the risk? No. There's another important real life pluralism scandal involving German defense minister. He pushed over PhD plagiarism scandal. He was a minister, defense minister. Then when it is reported that in 2011, was it reported, then he resigned from about it. Was it an important example is the President Joe Biden. Actually, President Joe Biden had fallen foul of plagiarism. He failed a course course written in law school because he plagiarized homework 5 page. The New York Times explained, Biden said that he used 5 pages from a published law review article with quotation or attribution. In an article he wrote, the Fordham Law Review. In 1988, Joe Biden was forced to withdraw from the presidential race due to this plagiarism allegation. So think about it. Take example in mind. What important it is. Other real consequences is it what it is? I'm asking. Pioneering physics paper is under such explanation and given retraction. The paper was retracted also. A massive case of fraud in India. A professor of Sri Venkateswara University professor was banned from taking any research guidance and work after he was found plagiarizing and used research papers. You can see the paper report there. 70 research papers published in a wide variety of scientific journals between 2004 and 2007, according to documents from his university, which were obtained by CNN. Some journals editors left feeling so this is a serious case, huge, massive case of fraud in. So, seeing all this, how to avoid plagiarism? It is simple, quite simple. The best method for it is to simply be honest. When you have used a source in paper, give credit where it is due. Acknowledge the author of the original work you have used. Another thing, citation, abolition. Is asking, do you cite everything? No. Right? The facts that are widely known or information or judgments considered common knowledge. So you don't have to cite those things. And example of common knowledge for students actually is a statement. John Adams was the second president of the year. So this is commonly known. So you don't have to, if you write in your thesis, then you don't have cite it, give citation for it. Further on citation, proper citation will be given immediately after every idea or fact that derives from another source. Acknowledge direct quotes or statements with quotation marks. Some facts are considered common scientific knowledge and do not need to be cited, as I have told before just now. Self-plagiarism. So complete reference is at the end of the paper. When citing online resources that are not available in print, include the websites and the date the information was found. Further on citation, any citation you give, read the work before you cite. Important to cite the work correctly and completely. So trails reveals the reference, go unread by citing authors. So editors have detected these things. So this was published in Nature, 20 volume, December 2002. Copyright definition. You know, copyright definition, exclusive legal right to reproduce, publish, and sell the matter and form of a literary, musical, artistic work. Note that this includes the scientific publications. Copyright protection is extended to anything that is fixed in a tangible, an article, email, message, website. So, as a student or research student, you write paper, you give oral and poster presentation. Possibly in this seminar, in this conference, some of you have done this. All text should be in your own words. Ideas or data taken from other sources should be cited on a slide, preferable or orally. internet connection is unstable. In the case of presentations, material in a bibliography similar to a written paper. Any figure produced by the presenter in an oral presentation or by the author, a poster presentation must be attributed. Permission to use a copyright matter, you have to take it. So let me go ahead. Conflict of interest. There may be conflict of interest when a researcher, author, editor, reviewer has a financial, personal interest or belief that could affect his or her activity or appropriately influence his or her actions, a potential conflict exists. You have to state this. Such relationships are also known as dual commitment, competing in or compete loyalties. Some people actually require this to be announced. Some ethical principle. So summary, honesty, you have to have honesty. I'm not explaining all this honesty. What does it mean? You know it. Objectivity, you have to, then integrity, you have, then carefulness, you have to be careful. You have to openness, share data, result, ideas, tools, resources, be open to criticism and new ideas. Just intellectual property. So you have to, and confidentiality. Then you have to be responsible for publication. Avoid wasteful and duplicative publication. Social responsibility, you have strive to promote social good and or mitigate social harms through research, public education, and competence. Maintain and improve your own professional competence and expertise through lifelong education and learning. So this clapping is due to you are publishing your work, a PhD student. So why publish? A paper is an organized description of hypothesis, data, or conclusion intended to instruct the reader. If your research does not generate papers, it might just as well have been done. Like authors said, if it wasn't published, it wasn't done. Published na kule ka Quran. And for PhD students, some excuses. Some do teacher doing PhD or others doing PhD. And what some of the cases I have noted, article writing is too time needed. And then I'm too busy with extra work, film capture and others. And then my CUET supervisor expects too much if you're doing PhD or other work in CUET or any other. Then I have got to get a promotion. So I have to look at that. I have to surpass my colleague at work. Plagiarism is asking, it's okay, you get caught. Some research, some researchers do it. Don't do it. So this is the order of the day. This is the examples I have real life to. Then conclusion is the rationale for academic integrity. And this fellow says, my academic reputation is valuable to me. So reputation should be there. Should not be there. When you copy, you cheat yourself. You limit your earning. The consequences are not worth the risks. It is only right to give creditors whose ideas you use. Citing gives authority to the information you present. Citing makes it for your readers to locate your source. Cheating is unethical behavior. And research ethics is an integral part of graduate research. Statements, figures, etc., etc. You have to be care about the things I have discussed. So again, your academic reputation must be valuable too. So as he says, I must be serious and active. Reputation is valuable to me. So be serious and active, PhD research. Useful tips to succeed in graduate research. Be selfish. That means you are working for a degree program. You think yourself to advance your knowledge. See a weekly goal the progress routinely. You have to minimize the time on internet for non-scientific logic. Just because you are sitting at your desk does not mean that your day was productive, happy. But remember to put in minimum to 8 hours per day for PhD work, although more time than this is necessary. It is your PhD. If you do not take interest or put hard work into it, nobody else will. This is an exciting time in your career. Make it a worthwhile effort. This is that. So, my acknowledgement is that web sources and materials used in this slide presentation are gratefully acknowledged. So thank you. I hope good things happen for all who are participating, students, post MSc student, PhD student, MPhil student. Thank you all. Thank you. Allah Hafiz.
Okay, thank you very much, sir. So for your valuable talk, and this talk is very important for all the researchers. Nowadays, we are lot of plagiarism cases are happening in Bangladesh in various universities. We should be aware of that. So actually, we are running behind the schedule. So we'll take one or two questions very quickly, or comments. Professor Belal raised his hand.
Thank you, sir, for giving me the opportunity here. I thank you, Professor Azharul Islam, sir, for your nice and wonderful, unique presentation here. Actually, I know sir very well, but I am not directly connected with him with research. But during this conference, as a session chair, when I communicate Professor Azharul Islam, sir, actually I here added this sentence to the audience, our young researchers. So how serious Professor Azharul Islam, sir? Actually, we want to give him keynote speech for first time at 9 a.m. So, but at last we think organizing committee that sir is old age, that's why we give him time. But when we discuss with Professor Azhar sir, sir said that after Fajr prayer, most of them sir doing writing, research, and writing books. Few of them just for 1 hour he take rest. And today when I enter, I think Professor Azhar sir for the first time entered the virtual platform. So thank you, sir. Sir, may Allah long live and keep us and doing for Bangladesh. Actually, the theme physics education and research, such type of research, sir, Bangladesh need more. Thank you, Azhar sir.
I actually appreciate the effort of the physics department of CUET doing this type of conference, webinar, in physical presence also. I also attended some, actually, at least one. And physics department, like, they are doing great work. Professor Mominul Haq is my friend. I visited him during his time. I know him. We also worked outside Bangladesh together, and it's good that Professor Basit said something about him. Thank you. Remembering, I saw his picture after a long time. So thank you, and I thank CUET, the organizer, and other person, Professor Dr. A.K.M. Akhtar Hussain. I know his work. He's a very good worker. Also the PhD from Imperial College also?
Yes, sir.
I was also PhD from Imperial College. Wife also PhD from Imperial College. My daughter PhD from Cavendish University. So, and son-in-law also, and the Saleh Hassan Nuki also son-in-law. So thank you all. I'm very happy to see all you here. Belal Hussain and Good luck to them, wishes for them, best health for them during this COVID-19. Thank you. Assalamu alaikum wa rahmatullahi wa barakatuh.
Wa alaikum salam. Okay, so we have another session. Actually, it is supposed to start at 11, so we are running behind the schedule. So let me summarize this session. So in this keynote session, there are three talks. First one was by Professor Hibbert, and he talked about nano optomechanical system for measuring very low level mass. Okay, and he can using his device, he is able to measure about 50 AMU, 50 atomic mass unit, and they have planned to make some device which is capable of measuring about 1 AMU in near future. That was a very wonderful talk. And then in the second talk, Professor Basit talked about perovskite type of nanomaterials. So he talked about various synthesis types, and also characterization technique of various types of nanomaterials and their multifaric behavior as well. And then in the last talk, Azhar sir presented about the present status of all over the world. Actually, plagiarism is a very big problem in nowadays. Okay, so he talked about the how to keep the integrity and avoid the fraud, fabrication of data, and falsification, and all other misconduct. So we should avoid from those misconduct. So I would like to ask our co-chair, Dr. Shopan Roy, to conclude the session.
Thank you, Professor Dr. A.K. Makhtar sir, for your kind presence. So we have heard a lot of scientific contribution. So no appreciation is enough for Professor Azharul Islam sir. Professor Basit sir, he is doing a good research, we know. My supervisor, Winnie Haber, he also showed some cutting-edge technology, as you pointed out. So now the next session will be started on, and I will introduce all other people. So before this, as a chair, sir, may I would like to request to end up this keynote session. Akhtar sir, please.
Yes, yeah, okay. And let us thank all the speakers and audience as well. Okay, thank you very much. So our next session will start now.
Yeah, thank you.
Okay.
So, Professor Mohiuddin, you are facing some trouble. Then please announce it first. Sorry for inconvenience. Just 1 minute.
Dear audience, you know another parallel session, nuclear and physics 1. So we think that there are many participants who have the oral talk at that session. So you have the parallel, we have the parallel link. You can log out from this session and log in the another session. Then you can get another Zoom link. So for your competence, we have given this link, chat box, and log in that session. We don't find the many author for that session.
I think this is okay. Those who are going to present their paper in nuclear and health physics 1, please log on the parallel session Zoom link. So now, may I request Professor Dr. Saleh Hassan Nakib from Rajshahi University to chair the technical session 1 on condensed matter physics 1. Nakib sir.
Assalamu alaikum and a very good morning to you all. Can you hear me?
Yes. So before going to provide the charge to run the session to Professor Dr. Saleh Hassan Naqib. I want to say a few words about him. He is an influential physicist in Bangladesh. He received his PhD from Cambridge University. He is working on superconducting materials or superconductivity or experimental low-technique physics, and also his contribution spans in different numerical analysis such as density functional theory. All his contribution makes him able to get the fellow position of the World Academy of Science. So dear audience, give hand to Professor Naqib. I got this opportunity. I think it's a great achievement for him. So thank you, sir, to make us proud. And as a co-chair, I announce my colleague, Dr. Mohammad Ashraf Ali. He is an associate professor in our Department of Physics, CUET. He received his PhD from the Department of Physics, CUET. His supervisor is Professor Mohiuddin. And the great news, we are proud of him. He got the World Academy of Science Fellowship just this year. So also congratulations, Dr. Ashraf Ali. I hope you two can make the session interesting. In this session, we have one invited talk from Dr. Unkul Goswami, Iit Delhi. He is also talk on the motor oscillator in MEMS-based resonators. So we are getting another mechanical resonator-based presentation, and there are other 12 contributory papers. Thank you all. So Naqib sir, please go ahead.
Thank you very much, Dr. Shapon, for your nice introduction. For this session, as Dr. Shapon Kumar told us that we have one keynote speech and 12 contributory papers. The session will start with the talk by Dr. Unkul Goswami. I would like to say a few words about his research and research career. Dr. Goswami is currently an assistant professor at Department of Material Science and Engineering at Iit Delhi, India. Before joining Iit Delhi, he was a postdoc fellow at Department of Chemical and Materials Engineering and Electrical and Computer Engineering at the University of Alberta, Edmonton, Canada. You can find the further details of his research career in the abstract book. So far, he has authored and co-authored more than 45 papers in peer-reviewed journals, and his publications include some articles in Nature, Nanotechnology, Physical Reviews, Acta Materialia, Advanced Materials, etc. He is also a reviewer of several international reputed journals, which includes, as I said, Nature Communications. He has advised 4 PhD students and 2 masters and several interns till date. So in this session, the co-chair will be Dr. Mohammad Ashraf Ali. I would request Ashraf to keep an eye on the timing of the lectures since we are running a bit late. So without any further delay, I would request Dr. Unkul Goswami to proceed with his presentation. Thank you.
Am I audible now to all of you?
We can hear you. Yes.
Okay, and my screen is visible to all of you, I believe.
Yes, it is.
Okay. Yeah, so thanks a lot for inviting me for the conference, ICPSDT, and I wish all of you a very wonderful luck about the conference. And I first of all, let me thank Professor Shapon Roy, who is also my colleague over at Alberta while doing postdoc. Professor Naqib, thanks for this nice introductions about me, Professor Ashraf Ali of the co-chair. And now let me talk about what we are actually going to discuss in this talk. So my job is a bit easier because Professor Wayne Hibbard already talked about resonators, And Professor Basit also talked about a lot of material science about his ferroelectric materials. Although I'm not going to talk about too much on ferroelectric materials, but it is on the condensed matter physics or Mott insulators. So my job is to couple this materials and the resonator together, and which can be fantastic observations which we have made. Right now we are trying to find certain applications, although we are saying that there can be possible applications, certain sectors like image recognitions and machine learning kind of things, but still that is a very preliminary stage. However, what I am going to talk about, like the initial results which mostly I have done in Alberta, and some of the part which after I joined here, we have started. So this is Iit Delhi. This is the campus, which is around 350 acres area, and we have a students of around 8,000 students, so including undergrad, postgrad, PhDs, and master students. And this is our department, which is actually 3 years before we have started Department of Material Science and Engineering, which was not there before that. There are multiple departments, but this is one of the departments which recently started. Professor Ram Gopal Rao is our director. And this is my group. After I joined here, we have established around 7-8 PhD students, which we are working with me. So so there are a lot of opportunities about interacting with the different countries we have, and I'm sure that in future if we have kind of collaborations between CUET and Iit Delhi, I'll be more than happy to be part of that. So with that note, I just want to go to my talk. So outline of my talk, which I'm going to talk about, what is basically a resonator, specifically mechanical resonators, which can be defined how it is, how microstring can be useful, and we are using a vanadium oxide as a material, and why it can be utilized such kind of resonator. How one can synthesize vanadium oxide? We made kind of thin films in this aspect. Fabrications of VO2 coated microstrings. We couple this vanadium oxide material or the oxide material as a thin film form on the microstring, and trying to understand what kind of resonance frequency we're going to observe. Now, the fourth applications, which is one of the key part of this talk, is how electrically and optically these microstrings can be resonating or can be stimulated, and one can change the range of frequencies over making these kind of functional materials. So most of the cases you see, these all resonators are of a standard silicon-based platforms and silicon nitride-based platforms, which only one side or the frequency changes goes one side. Here will
Professor,
your slide is not changing.
Oh, really?
Your slide is not changing. Please, slide is not changing. Only first slide is showing you.
Slide show.
See only first slide and next slide.
Is it
not seen yet?
I think you need to start all over again because the slide transition is not working. We are stuck with the title slide.
Is it my screen is visible now?
Yeah, your screen is visible, but we are stuck with the title slide.
Yes, initiated slide show.
So if I did a slide show now, is it visible?
Yes, yes.
Now if I change the slide, is it visible now?
No, it's not. So I request you to start it all over because you don't need to repeat what you have said, but the slideshow needs to be started.
Let me share. Resume share.
Yeah. Now we can see Iit Delhi.
Okay. So is it visible now?
It is visible.
Now if I change the slide.
Yeah.
Okay. Change the slide. Is it changing?
Not yet.
Okay.
I can see the second one. That is the Iit Delhi one.
Yeah.
The
now.
outline.
Okay.
The outline I cannot see.
Now if I go to outline, is it visible now?
Not yet. No.
Or is there a delay in my internet speed? Am I audible clearly to all of you?
You are audible perfectly well. Yeah.
Okay. Okay, now you can see possibly. Is it visible now?
No, if you want to do the slide, yeah, now we can see the outline.
Okay, I think that is the interface which is, now it is fine, right? If I change the slide.
It's good.
Okay. Sorry for the interruptions. Okay. So this is actually what I am talking about. This is Iit Delhi, and this is our department which we have started. So I'm not going to repeat too much about that. So this is the outline of my talk. We are going to talk about the resonator, the mechanical resonator, and coupled with vanadium oxide. So the vanadium oxide is a kind of a Mott insulator. We are trying to couple mechanical resonator and trying to couple these oxides, whether how they are going to behave with this material. Now we are trying to stimulate these resonators with putting electrical and optical fields into it and see what kind of potential applications we can find it out. And we saw some interesting phenomena which we'd like to discuss in this talk. So for the very preliminary part, that what is resonator? The resonator is a device that can exhibit resonance and resonating behavior, and which can oscillate at a certain frequency and amplitude. That's the very fundamental definitions of a resonator, and every resonator has its own resonance frequency. Now, it can be electromagnetic, mechanical, and so on and so forth. Now, this is a resonator. You can think of a clamp beam or a bridge where actually this bridge is mounted by two edges, and this bridge can move in any kind of directions. Like this way, there are different modes of the bridge. So all these resonators have different modes. Guitar string is also the similar way. Similarly, electromagnetic helical resonators are also the kind of resonators which people can think of. All these resonators have these fundamental resonance frequencies which can actually resonate at a certain frequency depending on what is the range it should possess. So all these resonance frequency can be varied depending on the materials you are using, from the hertz to the megahertz or gigahertz, what kind of applications you are doing. Now, string resonators, when I talk about the string resonators, this is a kind of a doubly clamped fixed beam which can resonate on its own resonance frequency, that can be surface, that can be across the perpendicular directions, depending on what mode it is. All this resonance frequency depends on its stiffness and this mass, and these are the kind of different modes of vibrations of these resonating strings it has. So in our this work, we are trying to focus on the cantilever and microstrings, which are the fundamental two devices we are going to talk about. Now, when we try to find out that what kind of frequencies one can get for this resonant behavior, we can get from the Euler-Bernoulli equations, very fundamental equations. And if you solve these equations, you can find out the eigenvalues and eigen vectors of that. Those eigen vectors, whatever you are getting, that's the modes of the resonance behavior, as you all know. So, and this resonance frequency depends on the material's elastic modulus and moment of inertia. So that means one is geometric factor, another is the materialistic factors, which one can tune these devices by making the structures and also the changing the material. So the resonance frequency, now if there is actually certain masses deposit on this kind of materials, what is going to happen? There is a mass absorption and therefore change in the mass, changing the frequency. So one can, by changing these frequencies, one should be able to measure what is the change in the mass. So that means that's what Professor Hibbert said in the previous lectures. And also thermally, if you change the stiffness by heating or putting a laser light, one should be able to change this frequency. So that means we have a stimulating part, which is like what kind of stimulus you are going to give into these things. One can change these frequencies in this case. When I say the change in frequency, we are talking about dynamic mode. If it is a static mode, that means only the deflections we are going to talk about. But in this lectures, I am going to focus on the dynamic mode of those cantilevers. Now, one of the cases, except the frequency, the other part is the quality factors. Quality factors is we say the fundamental frequency divided by the bandwidth of this one will give you the quality factor. When if there is the device is going to damp, we are going to get a large quality factor. So that means if you put this cantilever or string inside a kind of a water or any kind of damped atmosphere, this is going to get damped and therefore the quality factor broadens. So in order to get a better sensor, one should have a better quality factor. Also, Professor Hibbert said about that quality factors without changing larger quality factor can give you, but that was a separate talk which we have to see. So here we are focusing on the sharp quality factor and a certain frequencies, and try to understand that if there is a change in frequency, can we make a device out of it? Now, just to shift the gear, I would like to talk about what is vanadium oxide. The vanadium oxide is a kind of a material which possesses a moth insulating behavior. Now, the moth insulator is at low temperature, it has a monoclinic phase, and if you change the temperature to 68 degrees, it changes the state, its structure itself, which goes to monoclinic to rutile. In order to for happening these things, what is going to happen is that there's an electron correlations which are going to play a role. And therefore, there is a huge change in your electric resistance. And it has been established for last 50, 60 years that one can find out that how this last electric resistance are going to change over the period of temperature. And it is completely reversible. Now, for getting this vanadium oxide phase itself is very difficult because you have a range of different oxides which you can get. See the phase diagram, you can observe that there are multiple amount of phases exist. So getting phase pure vanadium oxide is always a challenge over a period of time. So what we did here, we are trying to talk about that, but before that, this is the vanadium oxide unary phase diagram where the temperature and pressure, if you change temperature and also the stress of the systems, you are going to change the phase transition temperature across this curve. That means if you increase the tensile stress, the metal insulator transition is going to change. Okay, so this is what actually this is did to establish this kind of resonating behavior. Before that, what we established here, can we get a phase pure vanadium oxide? In order to do so, we did a multiple Taguchi analysis in the PLD chambers and try to understand what is the particular temperature, pressure, distance, and energy required to get a phase pure vanadium oxide. So this one we have published and showed that 600 degrees centigrade, 50 milliliter oxygen pressure, 2.6 joule, we can get a phase pure vanadium oxide. Of this vanadium oxide which we have done is 20 nanometers. And we also showed that same technique, if you put on sapphire and silicon, we can get also a kind of epitaxial vanadium oxide. And in silicon, it is a polycrystalline vanadium oxide. We also did the transmission electron microscopy to show the interfaces of the vanadium oxide. We can see that in vanadium oxide, which is grown on silicon, you always have a polycrystallinity. But if you have on sapphire 001, it is a very nice sharp interface. You can get it. So now, if you see the sapphire on sapphire, it is very nice change over the temperature versus resistance. And at the same time, this vanadium oxide, what it shows that except, so this is the function of temperature, we are trying to find out what is the resistance change. Here, what we do is that in isothermally at different temperatures, if I do an IV, we see at a certain temperatures, it has changing its modulus or changing its phase transition, and therefore suddenly there is a jump in the electrical current. That means there is a kind of electric field emitting. That means the field if you are giving, that field is creating the Joule effect, and therefore there is a sharp change in your current, and therefore you get always a very nice loop over there, and this is completely reproducible and repeatable over the range of the voltage. Now, if you change the temperature, it will come down. Now, this is one of the fundamental things which we'd like to see, that giving electric field, can one tune this MIT and see in the mechanical response? That is one of the ideas which has provoked us. What we do here is we have a cantilever and put the vanadium oxide onto this. What happens because of this putting this vanadium oxide on this cantilever is mechanical frequency changes. Now you see here the bare cantilever is low mass, but with the putting vanadium oxide, the cantilever frequency has increased. Now supposed to be decreasing because mass has increased. However, there is a strain effect of the vanadium oxide which has deposited. Because of the strain, Euler modified Euler equations, one can see the frequency has increased because the strain factor has come into the picture. Now, what we do here, that now we did electrically a thin films and see whether electric, because of this electric field, the resistance is changing. What we now see that with the only mechanical modulus, that means if I do the measurement of this vanadium oxide's resonance frequency and monitor it, we see that room temperature, it has a frequency which is around 22.48 kilohertz of a cantilever, vanadium oxide deposit cantilever. As you increase the temperature, it can go further increasing. That means it is sharp increment of the stream. Now, had it been there is no vanadium oxide, that means only silicon nitride, what will happen is its frequency would have dropped drastically, because you are increasing temperature, your stiffness parameters, which depends on elastic modulus, is become softer. As material becomes softer, it should go down. In this case, what is happening is at certain temperature, there is a sharp change because of huge stress component come into the picture, and then it has stabilized, and then if you zoom it, there is like a drop of this frequency. So this is like a bistability kind of things, that the whole systems can change over, the frequency can be changed over in two different states. Now, what is the take-home message? We observe the MIT in VO2 through electrical measurement, which is in thin films, and we also see the mechanical. Can we couple with electric field and observe the mechanical modulus? What we do here is we make a simple string of silicon nitride and deposit vanadium oxide on that, and we showed that this kind of microstrings one can make. Now, in making these microstrings, what we do here that we probe these two microstrings by an electric field and observing its mechanical modulus now. So that means I am doing in room temperature measurement, trying to observe the frequency, giving the field whether there is a change in frequency. When I say giving the field, that means I can always give a DC field or AC field. First, we have given the DC field, and also AC field I'm not going to discuss here, which is a bit complicated, but let's see what is happening to the DC field. So at room temperature, we know that is here, and then high temperature, if we increase the temperature, it will go up. But can we now activate all this range of frequencies by giving electric field? What is happening that initially it was 360 kilohertz. As I am giving electric field about 6 volt, it is going down, right? But once I am actually in the case of 11 volt, which is larger, the frequency goes up. That means in the lower voltage, my frequency is in this range. That means my frequency goes down. At higher voltage, my frequency goes up. That means there's a bistability of these whole systems can be there. So by changing different DC electric field, one should be able to find out that the frequency of these devices can be tuned or can be modulated. And if I ramp up this voltage, I can see that whole systems are going under, first goes a cycle reducing and then go increasing. Any questions, or is that I can move forward? Somebody has, I'm audible, right? And visible.
Yes, you are audible. I think we should take the questions after your presentation is finished.
Okay. So now what we try to find out that we have done electric field. Now can we do by optical field with the light, with an external diode laser? Can we change these frequencies over there? It turns out to be that in except not only with the electric field, but optically also putting a external diode laser, one can change the frequency first in the lower like power, which is around 30 to 70 microwatt. And kindly note that power here, very minimal power of this diode laser can change the overall frequencies of these microstrings. So initially the frequency goes down, and then the frequency, there's a large jump in the power. So that also happens, this is with a red light, we can also do by green light, and this change over the frequencies are going to change depending on what kind of wavelength you are using, because depending on the wavelength, there's an absorption are different. So green light, and this is a blue light. And what we do here is, this is the multi-stability which we can activate. That means by giving an input light, if I change this input light, I can change the frequency in the downward or in the upward. So that means over the range of the whole systems, one can change this frequency. And that allows you to the multi-stability part of by using optical stimulus. Depending on different wavelength of the light, we can see that there is a lot change of frequencies. So what is the possible applications which we can think of in this thing, that the micro resonators, they have like, if one can change the different orientation frequencies, and depending on the power and light, one can do it in ultra fast switches. Why ultra fast? Because this is a very the power, the speed is at almost in the more than nanosecond, almost the picoseconds level it can happen. Although we cannot measure it, but we are able to do more than nanoseconds. We are not able to measure it. We do not have the device. So we believe at the ultra fast levels we can do it, and at the same time, because of this microstring resonators, we should be able to activate. That means we can, by input, I can change over the range of the frequencies. So one can easily do this kind of image recognition if there's a reference thing, and we have a range of like strings depending on the pulses of the optics, or even in the case of electric field. If we can do it, one should be able to find out the kind of image recognition one of the applications can do. Further and further, we are trying to evolve or find it out what kind of other applications are there, but this is on the initial level of our observations. So with that, I would summarize that microstring resonator is a device which allows to measure any input stimulus by changing its frequency in the dynamic mode. VO2 shows these metal insulator transitions, and we synthesize on the PLD, and also shown EMIT, and try to find out with electric field how the electric field and optical field, how one can tune both these frequencies in over the range. And we are able to detect this mechanical frequency changes under the electric field, which is around 20 kilovolt per centimeter of that range, because it is so small structures, the field is very high at even in the lower voltage. So we believe that this has a potential application in the ultra-fast switches, pattern recognition, and machine learning things if one can go into that with a large range of devices. So this is my acknowledgements. I think Professor Thomas, which we have worked to, Professor Ryan, Dr. Ryan, and Dr. Syed also worked with me, and Dr. Fahim Khan. These are all from the Canada and counterpart. And these are my students who have been also giving lots of effort these days and establishing these setups in the labs, trying to find out different kind of PhD problems. We are doing that, and I would like to, last but not the least, I'd like to give the acknowledgement to the grants, CRB and Iit Delhi Startup and SSPL, which has given funded certain part of this project. So if you have any questions, I would like to happy to answer. I'm sorry that I think a bit time I have taken.
Thank you very much, Dr. Unkul Goswami. You finished well within your time. So
okay.
Thank you so much once again. And it has been a very interesting talk because I have some personal interest on Mott insulators.
Okay.
I think the floor is open now, and I would like to take a few questions. I can see a raised hand from Dr. Mihir Kumar. So please, if you have any question, please ask. Dr. Mihir Kumar? Dr. Mihir Kumar Roy?
I think it is not audible, or yeah.
Okay, so if there is any other question from anyone else, please. Okay, if not, then I would like to ask you a very simple question.
Yeah.
You are using a Mott insulator,
yes.
But I think the main thing here is the metal insulator transition. Am I right?
Yes, that is what we are trying to.
Okay, yeah. So for metal insulator transition, even though Mott physics is very rich, but for metal insulator transition alone, there could be other more conventional systems. Am I right?
Yes, there are conventional systems, but I think the physics of this vanadium oxide is also rich in terms of whether it is a Mott physics or pulse physics. There is a confusion. You have asked the right question, because in this particular case, here one is structural transition, another is the electrical transition is happening. Although most of the people think in the Mott insulator the vanadium oxide is, but some people also say this is the pulse kind of insulator which changing because of the structure. It is going to happen. It's not the electron-electron correlation. However, some way I found more of the paper on the Mott side, so I have termed is that. But yeah, I think there are also nickel oxide-based Mott insulators are there, which is very rich, and also in the low temperature. Vanadium oxides, why we are interested? Because it is fairly nearly to the room temperature, and we can activate these things in the without putting any external stimulus or going to the low temperature. That is one of the reasons we are very much interested into.
Yeah, also I think the electric field induced effect is in my mind extremely important and very interesting. How you, yes. So is there any other question? Okay, if not, then I would like to thank Dr. Unkul Goswami once again for his wonderful talk, and thank you.
Thanks a lot to all of you, and I wish all the best to the conference organizer and the conference. We are happy to be part of this. Thanks a lot.
Thank you very much. I think now it's time we move into the contributory talks, and as far as I understand, the first presenter is not present here today, so we'll move to the second talk, that is CMP2. The title of this talk is Ab initio DFT Simulations on barium dope zinc oxide materials to investigate the doping effect on different physical properties. And as far as I understand, this will be presented by Mohammad Fatima Khatun Rajani. I welcome her to present her work, and I would also request my co-chair, Dr. Mohammad Ashraf Ali, to keep an eye on the time because we don't want to overrun. Okay, thank you. Mohammad Fatima Khatun Rajani. Rajani, are you there? Rajani, before you would start, I think you know you have 8 minutes for your presentation and we will have 2 minutes for question and answer. Am I right, Ashraf?
Yes, sir. Rajani,
we cannot hear you. We cannot hear you. রজনী তোমাকে শোনা যাচ্ছে না। তোমাকে শোনা যাচ্ছে না।
রজনী, আপনি কি শুনতে পাচ্ছেন? রজনী, আপনি কি শুনতে পাচ্ছেন?
Can you hear me, Rajani? Okay, Ashraf, I think
No.
She can't hear us. So perhaps
Sir, I think we can go
to the next talk. I think yes.
Yes, sir.
But if she is audible, we'll give her a chance to present her work at the last of the session, right?
Yes, sir.
So okay, so I'm sorry, we cannot hear her. So I'd move to the next talk, and it should be the third one, and the title is Improvement of Microstructure and Electrical Properties of Mg2+, introduced barium hexaferrite synthesized via spark plasma sintering. And this should be presented by MS Alam, Isao Kagomiya, and Ken Ichi Kakimoto are the co-authors. So let's move to the third one.
Okay. Can you hear me?
Yes, yes, clear.
Can you see my screen?
Yes, we can.
Okay. Thank you very much for giving me the opportunity, Honorable Session Chair, Co-Chair, and the audience. Assalamu alaikum and a very good afternoon. This is Mohammad Saiful Alam from the Nagoya Institute of Technology, Japan. I am presenting my work, Improvement of Microstructure and Electrical Properties of Magnesium Introduced Barium Hexaferrite Synthesized by Spark Plasma Sintering. So this is the content of my presentation. So I am working on ferrites. Basically, ferrites is easy to synthesize and it is cost effective. So ferrite shows high chemical stability with greater life expectancy, shows excellent electrical and magnetic properties, and ferrites has huge applications in the magnetic and electric fields. So what type of ferrites I am considering for research and why and how? So among the various ferrites, I consider the barium hexaferrites because barium hexaferrites exhibits these extraordinary features. Based on these features, so there are huge applications in this field. So among the features, I'm interested in the high electrical resistivity area. So I considered magnesium as a doped element in place of iron because iron and magnesium has different ionic sizes with different charge balances, which can possibly alter the chemical composition. And then redistribution of cation in various sizes is possible to make the holes or oxygen vacancy. This is the crystal structure, hexagonal crystal structure of the barium hexaferrite. And there are 5 different sites of iron, and so it's possible to occupy magnesium in the different iron or any one of the iron site. So to synthesize barium ferrites, there are very available literatures considering this synthesis process, but spark plasma sintering is not so much literature. So I'm interested in the spark plasma sintering approach. So I am briefly tell about the spark plasma sintering approach. So in the spark plasma sintering approach, graphite dye and the graphite pulse is used, and this atmosphere is the reduced condition, that is there is no oxygen, and considering this setup with the temperature till this one and pressure and with the high current with the low voltage, it is possible to make the dense sample. So I synthesized barium hexaferrite using the classical sintering approach, and magnesium doped barium hexafluoride using the both classical and spark plasma sintering method to observe the structure, oxygen amount, and electrical properties. So this is the classical sintering preparation flowchart. I sintered my undoped sample for 1200 degrees Celsius and magnesium doped sample for 1100 degrees Celsius, both for 5 hours sintering time. And using the sintered powder of magnesium doped sample, I prepared the sample, dense sample, using this setup and considering this pressure and temperature program, and use this sintering spark plasma sintered machine. So after preparation, I check the phase purity of my synthesized sample using the ordinary XRD and the synchrotron XRD. Then I did the read belt refinement using the full probe software. And I estimated the oxygen vacancy amount and the iron balances of the compounds. And for this, at first I collected the 1 molar hydrochloric acid, then 0.2 gram sample I dissolved in the in this solution, and I maintained the reduced atmosphere condition by flowing the nitrogen with the magnetic stirrer and the hot plate. Temperature, dissolved temperature is 80 degrees Celsius, and then more salt added, and the automatic titrator machine I used, and I considered these for the estimation. And surface morphology was observed by using the scanning electron microscopy, and the electrical impedance studied using this condition, and the electrical nature was observed by the ZBU software. So this is the XRD profile of my synthesized sample. I found that the single phase formed in my sample, this is SPS means spark plasma sintered and classical sintered sample, and this is my undoped sample. According to the ICSD data, this is a single phase formed. So the peak shift is now present here. So I think it is possible because the mixed balance of iron present in this composition, and which substituted magnesium 2 plus. That's why that is constant is almost similar. There is no change for this composition. And this is the read belt refinement profile of my compound. So from this profile, that is R values and goodness of factor, and this fitting parameters, I consider that the fitting is good, and I consider that tetrahedral site Fe3 sites because the R values and the other parameters is lower for this case. This is the mostly populated site. So I think magnesium is occupied in the Fe3 sites. So for the oxygen vacancy estimation, I consider this formula and this possible reaction occurred during the titration. So I evaluated the oxygen vacancy and iron 2 plus amount. I found that due to the magnesium doping, the oxygen vacancy as well as Fe2 plus is increased for magnesium doped sample, and which is further increased for the spark plasma sintered sample, which may be possible because of the reduced atmosphere condition. The oxygen vacancy is generated following this equation. And the amount of Fe2 plus I estimated from the Morsel titration, which is also supported by the read belt analysis, where I calculated that Fe2 plus is almost similar for the Morsel titration and the read belt analysis. This is the microstructural view of my synthesized sample. This is a polished surface image, and I found that the spark plasma sintered sample is most dense, which is more than 90%. And this microstructure view, that is dense sample and the porous sample of the classical sintered sample, is also supported by the density study. And in the after this, I considered the electrical study of my synthesized sample. I found that the magnesium doped sample is decrease the impedance, And for the spark plasma sinter sample, which is again greatly decreased. And this is similar pattern for all the 3 investigated temperatures. So also electrical nature I observed for this synthesized sample. I used the ZBL software and this circuit model, and I evaluated the parameters, that is grain and grain boundary resistance and capacitances. I found that with the increase of temperature, the grain and both grain boundary resistance decreased. And for the classical sinter sample, it is again decreased. And for the spark plasma sinter sample, magnesium group is further decreased. So I think the most density of this sample, and due to the increase of Fe2+, so it is possible to hopping between the Fe3+ and Fe2+ the electrons. And also I evaluated the grain and grain boundary capacitance. This value is close to this literature value. So overall effect of magnesium, I am concluding the discussed issues. The electrical conductivity increased due to the magnesium grouping, which is possibly due to the increase of Fe2+ in the synthesized sample. And then for the spark plasma sinter sample, I found that the electrical conductivity is greatly increased compared to the other 2 samples. So I think this is due to the high density of the spark plasma sinter sample. So this is the conclusion of my presentation. Thank you for your patience.
Thank you very much for your nice talk. I think we can take 1 or 2 questions. So if there is any question, please raise your hand. I can see a raised hand. I think it's Professor Mohammad Belal. Please ask your question. Professor Mohammad Belal Hussain. Professor Mohammad Belal Hussain, can you hear me? Okay, I don't think he can hear, but we have another question from, I don't know the name, it is CMP5. Please ask your question. CMP5.
Yes, sir. We have seen that magnesium has been used as a doping element, and the electrical conductivity has been increased very well. But my question, I have a keen interest to know, why did you choose magnesium particularly? What was the motivation behind choosing it before you started your research work? Is it more cost effective? Why not nickel or zinc? That's my question.
Okay. Thank you very much for your interest. So actually, these barium hexafluoride is the mostly studied material, but the zinc dope sample and the nickel dope is mostly studied, but magnesium dope sample in literature is not so available. I got only 1 literature that, but they didn't discuss the details of this one, and also they didn't study the electrical properties in detail. That's why I interested for this one. Yes, you are right. I also studied this magnesium, zinc dope sample and nickel dope sample, and also with the BS composition, but I didn't present here because of time limitation. Thank you.
Is there any other question? This would be the last one.
I think there is no other question.
Okay, so if not, then we should thank the speaker once again for his nice talk, and we should try to move to the next one. I think CMP4 will not present.
Thank you, sir.
Thank you so much. his work today. So we move to CMP5. The title is A Comprehensive Review Regarding the Technological Development of Zinc Oxide Thin Films from 2018 to 2021. It will be presented by Shubhra Roy, and the co-workers are Mohammad Mintu Ali, Mohammad Zahidul Haq, MS Rahman, Mohammad Nafiul Islam Sharkar, Ariful Bari Rifat, Shovik Shaha, and M. Humayun Kabir. So please, Shubhra Rai, the floor is yours.
Am I audible, sir?
Yeah.
Thank you very much, sir. Warm welcome to everyone present here, the chair, the co-chair, the respected authors. We'll focus on a complete, sorry, sir, maybe I have not started the screen sharing yet.
Yeah.
Okay, you can share.
Is my screen is sharing, sir?
Yeah, we can see it, yes.
Okay, sir. We will focus on the comprehensive review regarding the technological development of zinc oxide thin films from a particular period of time, 2018 to 2021. We are mentioning that it's a comprehensive review. It's not a fundamental work. We just studied a couple of papers and some of the conclusions that have been worked out. This is my presentation outline. We'll see what is thin film, its applications, why zinc oxide thin film particularly, basic properties of zinc oxide, different deposition techniques like sol gel process, spin coating, dip coating, spray pyrolysis, magnetron sputtering, and compare them, which is the best one. So this is Shubhra Roy, current student of Department of Glass and Ceramic Engineering, Rajshahi University of Engineering and Technology. So let us proceed. What is a thin film? Thin film is basically refers to the very thin layers of 10 nanometer to 2 micrometer of semiconductor material that are accumulated on upholding substrates. As you can see, the lower corner, there is a picture of thin film that has been deposited on a substrate, so it's very much understandable. Normally, zinc, gallium, aluminum, nickel, copper, indium, tin oxides are used as thin films or doping elements of a thin films. This distribution is actually done through controlled coagulation of ions, molecules, or gases through physical or chemical processes. So why is thin film so much important? What is application? It's pretty much common that we touch our mobile screen and it opens up. That means your screen is recognizing your biology, your fingerprint pattern. That is a major application of thin film. It is being used car glasses, microchips, solar cells, thin film transistors, photocells. Here is a table of the application of thin films: diodes, resistors, charged coupled devices, biosensors, gas sensors, thin film polarizing interference filters, LED. Everything, every site is now using this thin film technology for the betterment. Thin film technology has led to the low corrosion and low erosion protective layers, which protects valuable microchips from the atmospheric reactions. Now we'll see why zinc oxide thin film is so much important, why it is surpassing other thin film technologies. It has unique properties like thermal, chemical, and mechanical stability, which is very much important for being a thin film. With higher photostability, greater area of absorption, it has become a compulsory element in optoelectronic technology. Zinc oxide is a rigid, low-cost, non-toxic material, which is very user-friendly, with a wide band gap of 3.37 electron volt. Its structural tunability, piezoelectric and pyroelectric properties have expanded its uses as sensors, converters, catalysts in hydrogen production and power generation. You can see that zinc oxide can stay in 3 types of structures, like oxide, which is a hexagonal packing, zinc blend cubic packing, and rock source structure, which is very much versatile among other materials. Zinc oxide nanostrips is also 3 types. You can see that there are 1D, 2D, and 3D categories. nanorods are 1D categories, nanorods, nanoplates or nanosheets are 2D categories, and nanotripods, nanoboxes, these are 3D categories. All these three kind of nanosheets is seen in zinc oxide. So zinc oxide generally shows a C-axis orientation necessary post-deposition treatments, which is very much important for structural and propertical tunability, that doping with aluminum, indiums, tin, copper, gallium, these are very much possible with zinc oxide. Zinc oxide is an N-type material. It's transparent conductor and can also be used for detection of near ultraviolet emission. So these are the reason behind using zinc oxide thin film over other thin films more and more nowadays. So properties of zinc oxide has been included in this table. Here you can see that it has a very good melting point, 1975 degrees Celsius, a good thermal conductivity, linear expansion coefficient, static dielectric constant. So it's very much applicable. Different deposition techniques and how they evolved and comparison between them. Solid process, spin coating and deep coating. Let us see. Normally, sol-gel process refers to two terms. One is sol and the other is gel. What is sol? A sol is a colloidal solution, and colloid is a very much small particle dispersed in a liquid, and that sol eventually transforms into gel. We will see it further. So when the sol is formed, it can be, with this sol, we can do two types of job. First one, we can pour it into a container and make shapes like this nanofiber, as you can see in the screen. And the second job is we can deposit as a thin film, which is our main focus part. Here, you can see a comprehensive way of depositing a thin film through zinc oxide. So let us see. We are showing the deep coating method actually. Before deposition, how the colloidal solution is formed. Normally, salts, organic or inorganic, of zinc is used. Here you can see that zinc nitrate has been used. They form the colloidal solution or salt. When they are deep coated on the substrate, you can see there is a continuous network after drying. That is called gel. And it needs further annealing for better crystallization. Then we get a thin film. So here is another preview of deep coating. Deep coating is a very much easy and user-friendly process. You can see that the substrate which is intended to be coated is dipped into the solution directly, and after a couple of times, the substrate is taken out, and we find a layer of zinc oxide. And it's very much interesting that when the zinc oxide is coated, its property is completely different from its bulk volume. That means it develops properties which we need, but this kind of properties we don't get in the pure zinc oxide, which you get from nature. So spin coating is also a deposition technique, but here the zinc oxide or colloidal solution is sprayed on the substrate, and the substrate is spinned up, and it's continuously spinning up, and the extra colloidal solution is removed, and we get a